Saudi Arabia is betting more than $500 billion on a city built into a mountain, where summer heat can pass 40 degrees Celsius. If this works, it could redefine how cities are built. If it fails, it may become one of the most expensive engineering mistakes ever attempted. Saudi Arabia is building a city for winter sports in a place where summer temperatures in the surrounding deserts regularly push past 40 degrees Celsius. It is a project that promises snow, lakes, and alpine resorts in one of the driest regions on Earth. This is Trojena, a high-altitude mountain development inside the wider NEOM region, part of a national transformation plan valued at more than $500 billion. Trojena alone spreads across roughly 60 square kilometers of rugged terrain, carved directly into the Sarawat Mountains. Parts of the site rise to more than 2,600 meters above sea level, high enough for winter temperatures to drop below freezing, but only for short periods each year. Despite that limitation, Saudi Arabia has committed to hosting the 2029 Asian Winter Games here. From the very beginning, Trojena has posed a difficult question. Can engineers redesign climate, water, and geology at city scale and make them behave in ways nature never intended? Please take a moment to subscribe and like the video. It really helps the channel. Trojena is not being built on sand or flat desert plains. It is being cut into the Sarawat mountain range, a geologically complex system formed through millions of years of tectonic uplift, faulting, and erosion. The rock beneath the site is not uniform or predictable. It includes fractured igneous layers, metamorphic formations, and shear zones that are naturally vulnerable to slope failure. In some areas, gradients exceed 30 degrees, creating constant gravitational pressure on anything placed above them. Building a city here is fundamentally different from building in Riyadh or Dubai. Every structure must resist slow-down slope movement, sudden rockfall, erosion during rare but intense rainfall, and thermal expansion swings that can exceed 30 degrees Celsius each year. By geotechnical standards alone, Trojena already ranks among the most complex urban projects ever attempted. Before buildings can rise, the mountains themselves must be reshaped. Early satellite imagery reveals millions of cubic meters of material already excavated to form artificial plateaus, terraces, and cut platforms. For comparison, Dubai's Palm Jumeirah required around 94 million cubic meters of sand, dredged at sea level. Trojena's earthworks are expected to rival major global megaprojects, but they are happening in hard rock, at altitude, inside a fragile mountain system. Dozens of kilometers of tunnels are being driven beneath the surface to carry utilities, stabilize slopes, and embed structures into the rock face. Unlike conventional tunneling, these excavations directly affect the stability of everything above and below them. In this environment, margins for error are measured in millimeters, not meters. To stop the city from slowly sliding downhill, Trojena relies on extreme structural engineering. Buildings are anchored into bedrock using deep piles drilled far below the surface. Retaining walls, some potentially rising more than 50 meters, hold back entire sections of regraded mountainside. Multi-level terraces are reinforced with post-tensioned concrete, designed to counteract constant lateral forces. Engineers must account for differential settlement, where different parts of the same structure move at different rates over time. Roads, rail systems, and ski infrastructure cannot be rigid. They must flex without cracking. In mountain cities, maintenance is not a future concern. It is a permanent condition of survival. Even at altitude, Trojena does not receive consistent natural snowfall. To meet international competition standards, engineers must create winter artificially. Large-scale snowmaking requires hundreds of thousands of liters of water per hectare of slope every season, combined with sustained sub-zero wet bulb temperatures. High-pressure pumps force water through snow cannons, while cooling systems ensure ice crystals form before hitting the ground. The electricity demand alone can rival that of small towns. All of this is being planned in a region with no rivers, minimal groundwater, and annual rainfall that often falls below 100 millimeters. This transforms snow into an industrial product, manufactured at scale rather than delivered by climate. Every drop of water used at Trojena must begin its journey at the Red Sea. It must be desalinated, pumped inland, and lifted thousands of meters uphill to reach the site. This makes Trojena's water among the most energy-intensive in the world. Desalination typically consumes 3 to 5 kilowatt-hours per cubic meter before accounting for pumping losses. When artificial lakes, snowmaking, hotels, and residential demand are combined, the water network becomes a permanent industrial operation rather than a background utility. Evaporation increases at altitude, fractured rock allows leakage, and freeze-thaw cycles stress pipes and storage systems. Retaining water here is as challenging as bringing it in. NEOM claims that Trojena will operate on 100% renewable energy, supplied by solar, wind, and green hydrogen. In theory, generation is not the hardest part. The real challenge lies in delivery. Snowmaking, desalination, cooling systems, and mountain transportation create extreme peak loads, often when solar output is low and demand is highest. Meeting those peaks requires vast energy storage, whether through large-scale batteries, hydrogen buffering, or grid backup systems that are rarely discussed in public announcements. The question is not whether renewable energy can be produced. It is whether it can be supplied continuously at altitude during winter without interruption. The Sarawat Mountains support endemic plant species, migratory wildlife routes, and traditional land use patterns that have existed for centuries. Large-scale grading permanently alters drainage systems. Artificial snow changes soil chemistry over time. Constant water extraction reshapes aquifers far beyond the site itself. These impacts do not appear immediately. They accumulate slowly, often becoming visible decades after construction finishes. Engineering can stabilize structures. It cannot fully control ecosystems. Once altered, mountain environments rarely return to their original state. Trojena is designed as a luxury destination, built around international tourism, premium real estate, and global sporting events. But Alpine infrastructure is among the most expensive to maintain anywhere on Earth. Snowmaking systems, slope stabilization measures, water pipelines, and high-altitude transport networks require continuous capital investment. As temperatures rise globally, operating costs increase rather than decrease. The question is no longer whether Trojena can open on schedule. The real question is whether it can remain economically viable 20 or 30 years into the future, when climate pressures intensify and maintenance demands grow heavier. Today, Trojena is no longer just a concept. Satellite imagery shows massive earthworks, stepped platforms cut into the mountainside, and expanding access roads threading through the terrain. But the most critical systems have yet to prove themselves. Long-term water throughput, large-scale energy storage, and reliable snow conditions remain largely untested at full capacity. Trojena is under construction, but it is not yet a functioning city. Trojena pushes engineering beyond calculations and into philosophy. It asks whether technology should adapt environments or attempt to bend them to human ambition. If it succeeds, Trojena becomes a global demonstration of what coordinated engineering can achieve under extreme constraints. If it fails, it could stand as one of the most expensive lessons ever embedded into a mountainside. And for now, the final outcome is undecided. The engineering continues, the systems grow, and the mountain itself remains the ultimate judge. Thanks for watching Unthinkable Build. We'll see you in the next one.